So students, we now review the concept of a mixed distribution. So we call mixed a random variable which has a discrete part and a continuous part. Now, let's denote generically big X such a mixed random variable. We denote its discrete support. The support means the values that X can take that are discrete, meaning that for those values, there's a non-zero probability that X takes them. Now, for this discrete support, you might say that X has a PMF, a probability mass function that you might denote Px. Now, there's also, of course, a continuous support, denoted C here. And on that support, you might say that X has a PDF, probability density function, that here we're going to denote little hx. Now, I say those words in quotation marks because the sum of all the px's doesn't equal to 1. And the sum of all the hx's doesn't equal to 1. So strictly speaking, they are not PMF and PDFs. But still, it helps to view them as kind of, I would call them pseudo PMF and pseudo PDF. They don't sum to 1 because what we want is that both their sum equal to 1. Meaning, if you sum the probability to be on the discrete part plus the integral of this pseudo density hx on the continuous part, then you should get to 1. Because again, this 1 represents, it's 100%, meaning the random variable needs to be somewhere. So it needs to either be on the discrete part or on the continuous part. And so those two things need to sum to 1. Maybe good to see just illustration of this. Imagine then that our random variable x lives somewhere here. Now, on this specific example, it has two points that have a mass. Okay, so the discrete support would be x1, x2, because this is illustrated here. The probability x equals x1 is given here. Okay, illustrated here by a blue bar. And then the probability that big X takes the value x2 is here given by this bar. So it has this probability px2. Now there's of course also a continuous part, which is illustrated there. And here in this specific example, there's an overlap, you might say, meaning the continuous part, it would be this interval here on which this pseudo density hx is bigger than 0. Okay, and then this would be the continuous part. And you see, the integral of hx over its whole support, is smaller than 1, of course, because we need some positive probability that x equals x1 and x equals x2. Okay, now we can easily recover the CDF of x. Obviously, by definition, is just the probability that the random variable big X is smaller than the argument little x. Now, sum the discrete probabilities. So the probability that the random variable is on the discrete part, but smaller or equal to little x. And then add to this the integral of ht on the continuous part, but of course for which t is smaller than x. Now, if we can illustrate this with our example here, let's say that we want to find the probability that the random variable is smaller than an argument little x. Let's say that the little x is somewhere here, so that this is little x. So we need to find the probability that big X is smaller or equal to this quantity little x. Well, we would sum this thing, the probability that x equals exactly x1. We would sum to this the integral of hx from this value here up to little x. Okay, which would correspond to this formula here, px1 plus the integral on the support up to the value little x. Okay, of course, if little x was somewhere else, you would have something different. If little x was, let's say, here, well, then of course you would need to sum px1, px2, and then the integral on this part up to x. The other useful formula is the one for the expectation. So you can find the expectation of x or the expectation of any function of x. I've written this here as just gx, g being a generic function. You sum gx px on the discrete part, and then you add to this the integral of gx hx on the continuous part. Now, a specific situation or example of a mixed distribution is the following. That is especially relevant to us in insurance claims modeling. Consider, for example, the yearly amount claimed on a given insurance policy. Call this amount big X. Now, in a given year, it is certainly possible that no claim will be lodged. So on a specific policy, the amount claimed is exactly 0, and this happens with a positive probability. So a probability that is strictly bigger than 0. So you have what we call a mass at 0. But now, if a claim is made, then it is reasonable to model the size of this claim as a continuous random variable with a certain density f of x. Now, I call this a density, and this would be a density in the proper sense. Because, careful here, what I call fx is the density of the random variable x, but given x is bigger than 0. So the random variable x, under the knowledge that x is bigger than 0, this is a proper random variable. It is fully continuous, or here it's reasonable to model it as fully continuous. So then it would have a density in the proper sense of the word density. Now, under this framing, and with hx as defined before, can you tell me what is hx in this framing? Maybe pause the video, take a second to think about it. While you think, I'm going to just illustrate the simple case we have here, which is that at 0, we have a mass. Okay, so there is some probability that here I called P0, that the random variable big X takes the value 0. Now my illustration is a bit poor here. Let me cap another color for P0. But then everywhere else, the support is continuous. So everywhere else, you have some density. Which generically we called hx. But now I said that what we call fx is the density given x is bigger than 0. So hx doesn't integrate to 1, but fx does integrate to 1, and hx is just a scaling of fx then. Meaning they have the exact same shape, it's just that fx is a bit bigger because fx integrates to 1, while hx doesn't integrate to 1. What I mean is this: we must have that they have the same overall shape. It's just that hx is a constant times fx, a constant smaller than 1. Now, the only possible choice is the one that ensures that, of course, this property over there is verified. So basically, you need the sum on all the px plus the integral on hx to be equal to 1. We have that hx is just a scaling of fx. So then we have the integral of a fx needs to be 1. This easily simplifies to a is 1 minus p0. Okay, so this overall the conclusion is hx, you're just scaling back fx by the constant or by a factor 1 minus p0. Now, if it's not so intuitive to you why hx is just fx reduced by a certain factor, I think we can explain this with using a bit of calculation I put here. Now, it's a bit tricky, I suppose, because a density is not a probability, strictly speaking. But if you recall from your probability class, you can interpret a density as follows. Little hx here would be the probability that the random variable big X is in a very, very tiny interval around x, meaning it's a probability that x is bigger than little x and smaller than x plus dx. Now, dx is just a standard mathematical notation for a tiny, tiny, tiny quantity, but then divided by this dx. Okay, this you would find in a probability textbook. I mean, this is not entirely rigorous, but I just want to illustrate the intuition. The result would be that the more formal formulation is that this thing converges to hx, actually. Okay, converge. So if dx converges to 0, so for dx goes to 0, this thing here goes to the density hx. But now here, I just want to illustrate the idea. So it's not, I suppose, entirely rigorous, but I'm going to put equality here. But then I just want to illustrate this. You can understand using conditional probabilities, because now, this is a probability. You can condition on any event you like, but in our case, the event of interest is x being either 0 or bigger than 0. So this is the law of total probability. Take the maybe I should write this as a reminder. The probability of anything, okay, A, you can always say it's probability of A given some other event times the probability of that event, but then plus the probability of A given the complement of that event times the probability, of the complement of that event. Now, this is exactly what we're doing here. Our event here, B, would be x bigger than 0, then times the probability that x is bigger than 0. Now, I haven't added the other bit, but the other bit is just 0 here, because here I'm under the condition x strictly positive. So then the other bit, probability that this happens, if I know that x equals 0, this is 0. Okay, but then now look at this expression. Under the knowledge that x is strictly positive, this whole thing is just the density that we call little f of x. Well, yes, because by definition, this density, little f of x, is the density of the random variable x, given that x is bigger than 0. So you look at this, it is the density that we call fx. And then this gives you the results. Hx is fx times the constant 1 minus p0. But now, if this doesn't convince you still, and you were very happy with this, stick with this. That's fine. Okay. In the end, I just wanted to make clear that the hx is a rescaling of the fx. Okay. If this is all a bit abstract and theoretical, hopefully a real life example will help. So the example involves our friend Josephine, and so she's still in her quest for love. She's still going on dates. Now, the probability Josephine has no dates in any given week is 75%. Unfortunately for her, but it still leaves her, 25% of weeks she has at least one date. If she has at least one date, then the time spent on dates is exponentially distributed with a mean of 5 hours. So here we will call big X, the random variable, total hours spent on date in a given week for Josephine. Now you see, it's an example of a mixed random variable that has a mass at 0. So it's exactly like in the case that we explained over there. It's possible that Josephine has no dates in a given week, in which case the time spent on dates is exactly 0, and this has some positive probability. But now, if she goes on at least one date, then the time spent on dates is continuous. So it's exactly an application of this situation. Now, a few questions for you. Find the probability that x is bigger than 4. Find the expectation of x. Find the standard deviation of x. Sounds simple enough? Well, if so, take a moment, try to do those exercises, and then resume with the video. Do it. I'm serious. Now, in my case, I'll go to the solution. Now, the first one is the probability that x is strictly bigger than 4. Now, if we want to use the same notation that we used before, the hx, the pseudo density on the continuous part, would be 1/4 the density of an exponential. Well, yes, because this would be what we call fx, the density of the random variable time spent on dates given, given it's strictly bigger than 0. And this is probability 25% to happen. So this explains the 25% here. Now, with that set up, I think we can easily answer the question. Probability that x is smaller than 4. Well, careful. You need to start with the probability that x is 0. So, of course, 0 is smaller than 4. And then you integrate the hx over the full support. Well, not the full support, but the support that satisfies this condition x smaller than 4. So you integrate from 0 to 4. Now, this is easy because obviously this is the density of an exponential. So if you put the constant in front, the 0.25, I mean, you know that the cumulative distribution function of an exponential has a simple expression, which is this. Meaning, well, well, in general, I can write it here for your convenience. Big F of little x would be 1 minus e to the minus lambda x. For us, the lambda is 0.2. Sorry, I didn't say why, but 0.2 is because we know the mean, right? We know that there's a mean of 5 hours, so we know that expected value of x is in the case of an exponential 1 over lambda. If this is 5, obviously it means that lambda is 0.2. Okay, so we have our 0.2 over here and our 4 here, which corresponds to the little x there. And you get to this numerical value. You can also compute it with your calculator to get to this value expressed in decimals. Sorry, let me just take a sip. Now that's for the probability. The second question was the expectation. I use the word expectation. You could call this expected value. Maybe I'll switch back and forth as well. Means the same thing. Now, you can apply your formula over there. You know, you will sum all the. Well, here it's just the expected value, right? So there's no g here. So you just take the good old expectation. You sum all the values times the probability, then the integral of the values times the pseudo density. Okay, so you have the value 0, which is probability 0.5, and then 0.25. Now you integrate what? Well, you integrate the density of an exponential with mean 5. This is why you have a 5 here. So that's good with this. And then lastly, you need the standard deviation. How do you get to the standard deviation? Well, of course, you need the variance. And how do you get the variance? You need expected value of x squared. Okay. Now, expected value of x squared is also found with the general formula. Over here, it's just that our gx would be specifically x to the 2, x squared. And so again, well, the only discrete part is the 0, so 0 squared is still 0, so this disappears. And then again, you have your constant in front, the 0.25 that is here, and then you integrate x2 times the hx. Well, sorry, times in this case fx, because I've put the 0.25 in front. But again, this is easy because we know fx is the density of an exponential, so we know that the integral of x2 times the density of an exponential is this. Where does this come from? Well, it's simply the result of expected value of x squared, where x squared is specifically an exponential with a lambda of 0.2. You can go, let's go back to the section about continuous distribution. This formula is given as is. Here, expected value of an exponential squared is 2 divided by lambda squared. Okay, this is exactly what is in the solution. So back over there. This is the 2 divided by lambda squared. Okay, you compute this, you get to a nice number. Well, I don't know if this number is nice, but it's at least, it doesn't have too many decimals. 12.5. This is the expected value of x squared. You find the variance easily by taking expected value of x squared minus expected value square outside. You take the square root of this. Obviously, you get the standard deviation, and you are done. And you can do, well, something else productively with your time. For now, I'll say bye-bye, and I'll see you in the next video.